So what we're going to do today is discuss pi, that universal constant that as math teachers we tell our students about from a quite early stage. So for example, if you go to Epsilon stream here and you key in pi, you get a few selected videos that our team has selected about pi. There's also a tag experiments to determine pi and things like that. So pi is everywhere and everybody deals with pi all the time. How about coding pi? So that's what we'll do in JuliaBox and Julia, and let's see how that works. So I'll go over to JuliaBox. For those of you that have seen the previous versions of this series, you might have done this already. And if you're doing this for the first time, then just try to follow along and see how it works, and then maybe try offline a bit later. So I'm authenticated in JuliaBox in this way through my email, Math Teacher's Code in this case. And I'm logging into JuliaBox. And as this sets up, I'll also speak about a few other things. So I'm going to launch JuliaBox as we've done before. In the meanwhile, let me go to this tab. If you search for this video, I'll also put a link in the comments. So this is a video by Jane Harriman of Julia Computing. It's an intro to Julia tutorial. It's a very good tutorial. It's long. It's 2.5 hours. And following it and trying things might take even longer. But just for those of you that are wondering how to actually learn this language in a systematic manner, this is perhaps one good place to start. So that's that. So we're here in the Jupyter platform, and we see the two previous files that we had from Math Teacher's Code. And I'll create now a new one, and Julia 1.0. So we'll create a new notebook. And we'll call it Math Teacher's Code Session number 3. Okay, so that's how I renamed the notebook, and that's up there. And we're all ready to start. Okay, so what are we interested in? Well, before further ado, I'll just key in the constant pi, pi, and hit Shift Enter, and we get pi. Pi equals 3.14159, etc. Pi is coded in Julia. Already it's a reserved keyword, pi. Now you can also, I'll link, I just got here some two other blog posts that I'll link in the comments. This one, some fun with pi and Julia, and that does exactly what I did now. So this is by these guys. And also some Piography, another blog post associated with pi and Julia, with a bit of kind of historical context of pi, etc., and all kinds of different ways to compute pi, which is what we're going to do today. And there's even, I was told about this way of computing pi, which is using differential equations. This is another example in Julia. So I'm throwing a whole bunch of things at you, but in a second we'll do pi in a very simple manner. We'll calculate pi in a very simple manner. So I'll put this link too. So this is just a few hours before, a few hours ago, these links were suggested to me. And this is a fourth very nice blog post, Monte Carlo simulation of Buffon's needle, which is a randomized method to obtain pi. One of the virtues of this method, it kind of just shows the usefulness of actually using random numbers to compute things that are not random. So that's a nice blog post, also discussing computation of pi in Julia, etc., etc. And the web is littered with many, many other resources for pi. All right, but our goal is slightly different. We want to compute this in a rather, well, in a few straightforward manner, in a few straightforward ways, and with a view of thinking that we can do this in front of our K to 12 students. When I say K to 12, this is probably suitable for grade 4 and above, and points are probably really driven home by middle school or slightly above. But let's just see where we go with it. So before I go any further, let me just create this markdown cell and just remember that area of a circle is pi r squared. Okay, that's an area of a circle. So what I did here is I wrote pi r squared in LaTeX, and when I did shift enter on this markdown cell, it formatted the LaTeX. If you don't know LaTeX, that's okay. That's not crucial at all for getting this to work. This is just commentary. And the circumference, that's pi d or pi 2r, if you'd like. There are different ways to write that. Let me just write it like that. Okay. So of course pi appears in the area of a circle. Now, the first way that we're going to compute pi is actually completely not related to circles, and later on we'll actually plot some things and see how circles pop up. And this has to do with this remarkable formula that Euler discovered. And here it is. It has to do with the value of this series. So what we have here is an infinite series, a summation of 1 over k squared when k runs from 1 to infinity. Okay, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc. And a few hundred years ago, it was discovered that this thing equals pi squared over 6, which was astounding and phenomenal at the time. This also happens to be what's called the Riemann Zeta function evaluated at the point 2. But that's not relevant directly for now. So this is a claim that if you sum up the numbers 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc., etc., you are going to get an approximation of pi squared over 6. So let me, for example, evaluate this. We get some number. If this is pi squared over 6, then it must be that pi equals the square root of 6 times this sum. So pi should be the square root of the 6 of the sum. So if I do 6 times this sum, and of course I'm now not summing all the way up to infinity, there are missing terms here, okay? But this is going to be an approximation of it, and I do square root of that. Square root is a Julia function square root, and we get an approximation for pi. Well, that's not a wonderful approximation. 2.9 is quite far from 3.14, but we're missing some terms. So if I add some more terms, 1 over 5 squared plus 1 over 6 squared, etc., we'll probably get a bit closer. Okay, and you see we crawled up almost to 3. With 1 over 7 squared will probably get us just past 3. And this thing will inch up into pi. Well, how do we do this, this whole thing in one line in Julia? For this, let me introduce something which I'm not sure that in this series of tutorials I've used before, and that's a comprehension. And the way comprehension works is I'm going to do some expression as a function of k, for k being the argument, for k in some range, for example 1 till 10. Okay. Now what do I mean by expression of k? Anything associated with k. For example, let's take k squared. So what this thing does, it creates an array of elements where for the first element it took k being 1, and that's 1 squared. For the second element k was 2, and that's 2 squared. For the third element k was 3, etc., up to 10 squared, which is 100. In this way I can actually create a list of the summons of this series that we have here. Right? I can make a list of these summons. So why don't I do 1 over k squared? and that would give me a list of the first 10 terms. Let me first just get the first 7 terms, just like we did in cell number 5 above. Okay, so this gives us the first 7 terms. This is a list of the first 7 terms. It's an array of the first 7 terms. If I sum up these terms, then what I'm going to get is exactly this expression. So let's look at that, and that is this intermediate expression. And then let us multiply it by 6 and take square root of all of that. And we've reproduced the same value that we did above. We're still not at pi, but of course now our life is much easier, right? Because we don't need to continue and write 1 over 6 squared plus 1 over 7 squared, etc. We chose here to sum up to the first 7 terms. Let's go up to the first n terms. So let n be 10, for example. That would be n. And these are the first 10 terms in Euler's series of 1 over k squared, well, when we sum them up and solve for pi. I don't know how far this was calculated numerically back in the 18th century, but probably not so far. So let's take the first 1,000 terms. And then, since the series converges and hence the term 1 over k squared must go to 0, the terms become negligible and we're quite close to pi. The 3.14 is still not the 3.1459, etc., but we can go for 10,000 terms, and then we're at pi. Or at least, well, we're certainly not at pi, but we're at pi for at least quite a few digits. Okay, this is in no way the best way to calculate pi. There are many other ways, most of them involving Taylor series of one form or another. You can read about some of these ways in this blog post on Fun with Pi and Julia. But the virtue of this is that if you get your students to believe this, well, they need to understand what sigma notation is, or maybe you just write it out, and you compute it, then you can show them how you get pi out of thin air, without any circles involved, by the way. Of course, there's also a bit of an algebraic step here, which was just multiplying by 6 and taking the square root to solve this equation for pi. And that can also be exciting for 7th or 8th grade students that have already kind of understood that equations don't necessarily come in the form of let's find x. In this case, it's let's find pi. Okay. So having done that, let's depart from series and actually go for a way which is perhaps much closer to home, and that is circles. So before we do anything else, I just want us to plot a circle. So for this, I'll use the PyPlot package. So using PyPlot tells the Julia kernel, please load the PyPlot package, which is already installed here in this Julia box installation. And then I can use functions from and other objects from the PyPlot package. Now, what we want to do now is we actually want to plot a circle. And I want to plot a unit circle. So everything we're going to do now will have to do with unit circles. So r, the radius equals 1. Unit circle. So first of all, how do we plot a circle? Well, let's think of a circle as a collection of points where the thing that unifies all those points is that their distance from the origin is exactly 1. That's our unit circle. And the x and y coordinates of these points are, of course, categorized or described by the cosine of the angle and the sine of the angle. Okay, so for example, cosine at an angle of 23, whatever that means, well, that's actually 23 radians, but that doesn't matter. And the sine of angle 23, I mean, this looped around the origin a few times. So this tuple is a point in the unit circle. Okay, this is a point in the unit circle that happens to be with this x coordinate and this y coordinate. Okay, I can also create, instead of a tuple, I'll create an array. This pair of points That's this. Now 23 was a bit weird. Let's choose the angle 0. So cosine of 0 and sine of 0 would be the point exactly on the x-axis, which is a point 1, 0. Now what if we were to create a collection of these points for angles going from 0 up to, whoops, let me just say it, 2 pi, okay? And just plot all those points. So how do we do that? So for this, let's continue to use this idea of a comprehension, but now let's have an array of arrays. So what I want to do is I want to do a comprehension where this A is going to be the angle, and I'm going to take the cosine of the angle and the sine of the angle, with the angle going from 0 at, say, steps of 100th to 2 pi. Okay? And this will be a collection of points in the unit circle. We'll call this a circle points. That's going to be a collection of the points. Okay, so we've used the same idea in the comprehension, only that now we're not letting k, as we had above, run from 1 to n, but we're going to let the angle A run on this range from 0 to 2 pi. However, I don't want to speak in terms of radians here. I want to speak in terms of degrees, simply because, well, pi is kind of what we're trying to create. So for pedagogical purposes, if you're doing this with your students, let's speak in terms of degrees. So let's go from 0 to 360. And that just means in steps of 1 degree. So we'll have here 361 points. Now, we cannot use cosine and sine with degrees, and students that are doing trigonometry are already aware of this, right? And as surely you are. Let's convert from degrees to radians, the argument going into sine and cosine. So that basically tells us, let's do sine and cosine in degrees. Okay, so if we didn't make any mistake, then if I run this now, so running by shift enter, and I need to do here so I got a mistake, a not defined, say 4a. Okay, so the syntax, you see 4 is highlighted as a keyword. It's for the variable a. When the variable a runs on the range 0 to 360. Let me run this again. Shift enter, run the cell. And what we have now is 361 elements in an array, and each element is this set of points. This array is actually an array of arrays, okay, where each individual array inside the array is a point. But that's fine. We could still get, for example, the 40th point in the array. If I would access the 40th point, that would be this point on the unit circle. So now let's plot these points. Now, to plot, we use the basic pi plot function plot. Now, what plot wants? It wants x values and it wants y values. That's the basic way in which it works. And to get this, what we're going to do is actually, if we apply the function first, which just takes the first argument of each point. So if we were to apply the function first to circle points, let's say that 40th point, it would give us just the x argument of that. And if we were to apply the function last to circle points, that point, it would give us the y coordinate of that. Now, we want to apply this function first and function last to each individual point. And if I'm going here a bit too fast, this is now getting a bit technical with how to work with arrays and with the broadcast operator, which I'm going to show in a second. Then you could use this part without getting into the full technicalities just initially. So I can apply the function first and last just to get the first point, or the first coordinate, sorry, and the last coordinate, meaning the y coordinate for each point. Now, I can also do this like this. I can use now first dot circle points. And what this does, it applies the function first to each element of circle points. So this thing is called the broadcast operator. So it's going to apply the function first to the first point, and then to the second point, and then to the third point, etc. So if I was to do this, what I get are exactly the x coordinates of the points. So in the same way, I can do last 2 circle points. And now I have the y coordinates, and then if I plot these, and let me put a dot here in quotes, and that tells plot to actually put points. And what we're going to see is we're going to see our points. Okay, that's our points. And if I was to change the whole thing, and let's just go in steps of 10 degrees, not 1 degree, so we get a few less points, and you see these are our points around the circle. Now you might be telling me, hey, this is not a circle, this is an ellipse. Well, the point is, or no pun intended, that the axes here are not, well, the aspect ratio of this image is not 1. Okay, the aspect ratio of this image is in a more natural default way. We can fix that by doing subplot 1, 1, 1 aspect equals 1. I won't get into the technicalities of this, but basically what it did, then it meant that the distance allocated on the screen for every 1 unit in the x direction is the same as the distance allocated in the y direction. So we've got now our circle points, right? If we were to go in steps of 20 degrees, these are circle points, etc. And if we're going to go at steps of, let's say, even 45 degrees, then these are circle points. Now, by the way, look what happens if I remove this. I remove this dot here from the plot. So I'm going to just remove this, and then our points are connected. And oh, well, you know, you have a polygon inscribed inside a circle. Okay. So this kind of invites the second way, which I want to show to calculate pi, and that's in a way a very classic, basic geometric way, and that's to think of a sequence of inscribed polygons inside a circle, and then to calculate the diameter of these polygons, and then as the granularity increases, let's say not like that, but like that, then we're getting something closer and closer to a circle, and then we get the circumference of this, or the diameter of this polygon converges to the circumference of this circle. So let's try and do this in a slightly systematic manner. So for this, we'll make a function which we'll call make points. Okay, so this we'll leave for our circle, and we'll say n, and n is how many points are in this regular polygon. So if you're looking to inscribe a regular polygon with n points inside a circle, since there are 360 degrees in the polygon, the angle between each two adjacent points on the polygon is going to be 360 divided by n. And then here we're going to now make a list of these points. So we'll let here k, which will be a running index, run from 1 to n. I'll fix this in a second. I'll start with 1 point. And here I want my point. Okay, so I want points. So again, how do I do points? I'm going to do the points in the same way we did before. So I'm actually going to copy this whole thing. That's a point. And now this point is going to be k times theta and k times theta. Okay. And there's a bit of something missing. We'll see that in a second, and then let's do end. Now, the last element of a function, so in this line 9 here, to do lines, I hit escape and L, and then I can continue to work. That's how you show lines in Jupyter notebooks. So the last line is a return value, but I can also write that explicitly. So do that, and Julia's not happy about something for k in 1 to n. Okay, so now we have our function make points. Let's let me just comment out for now this plot for a second and run this again, just so we don't have output in this subplot 2. The subplot actually created a blank output. So if I do, for example, make points 3, apply the function which we just created to 3, we're going to get 3 points. And these should be 3 points on the triangle. Okay, so let's plot those 3 points. So let's call points what we get from 8.3 and do another plot command like this. So that's plot the first of points, that would be the x coordinates, and the last the y coordinates. And let's actually put a red point with a dot. So this string as a third argument of plot from pyplot actually says to plot red points. And let's keep the aspect ratio. So you see we've got now our 3 points. Let's plot this together with the circle. So the first plot is meant to show a circle, and you see we've got now our 3 points. If I was to just keep a red without point, we've got our triangle. But wait, we actually don't have a triangle because we've got here 3 points but only 2 segments. If I was now to change this n here to n plus 1, that would mean to not take 3 points, but actually make 4 points, even though we're just speaking about a triangle. And then when plot connects the lines, it's going to connect. It's going to connect 3 points via 3 segments. Okay, and I can do this. I can now, instead of make points 3, I can do make points 4. And I can do make points 5. And we've got a pentagon inscribed inside a circle. Make point 6. And we've got a hexagon inscribed in a circle, etc., etc. Now, of course, the beauty of mathematics allows us to calculate an explicit expression for the diameter of these inscribed polygons as a function of n. But we don't want to do this. We actually want to just ask Julia to sum the distances of these lines that it just drew. So for this, let's create another function, first of all. And let's call this function dist. It's a distance between 2 points, and we're going to do nothing but implement the distance formula as it is known, or in my view, just Pythagoras' theorem in the Cartesian plane. Now, I must say that you don't need to really implement this function. You can use a norm function from the linear algebra package, and there are other ways too. But again, if you're doing this in front of a classroom, you actually don't want to necessarily bring in heavy machinery from concepts that your students don't know, because you don't want to speak necessarily about norms in grade 7, 8, 9, 10 even, or maybe even later on. But you actually want to just represent the distance formula. So what's a distance formula between 2 points, w and v? It's going to be the square root of the sum of 2 things. The first one is going to be w1 minus v1 squared. And the second term is going to be w2 minus v2 squared. Okay, this is now the distance function. Let's just check it. Let's do distance between the origin and the point 1, 1. So that's a square root of 2. Right? So the origin and the point 1, 1, that's the square root of 2. So now we've got the distance function. Now that we've got the distance function, this distance function gets as argument 2 points. Okay, so it assumes that it has 2 points, and it calls the x coordinates, the difference in the x, and the difference in the y. The 1 here stands for the x, and the 2 for the y. Again, arrays in Julia start with indexing at 1. Those of you that program in other languages too, often indexing would start at 0. Okay, so that's its distance. So now why don't we just create a comprehension which has these distances. Okay, so what we can do is we can think of all of the points for k in 1 to all the points that we have, minus 1. And here we're going to have the distance between the kth point and the kth plus first point. Okay, so this is now going to k is going to iterate from 1 until all of the points. Now we don't need to run, we only need to run on the segments. So there are n plus 1 elements in this array of make points, but there's only n segments because there are physically just n vertices to this point. So if we do this, then what we get is this collection of distances. Now, it happened beautifully that for the hexagon inscribed inside the unit circle, each distance is exactly 1. So that has to do with the fact that each of the triangles inside the hexagon is an equilateral triangle, and the side of the triangle is 1 because the radius is 1. Okay, so if we were, for example, going to speak about 3 points, then the sum won't be 1. Now you also see, even if we go back to the hexagon, you'll see a bit of a numeric discrepancy. So you'll see that this is 1.0 and this is 0.9999999, which of course if you'd continue this series forever, it does equal 1. But due to numerical, and this is slightly above 1, so due to numerical errors, okay, because real numbers are only approximately represented in the computer in Julia, and in any other programming language per se, unless you're doing things symbolically. Okay, so these distances are very close to 1, but not 1, but for all practical purposes, they are 1. So if we sum this thing up, we get the circumference of this regular polygon, in this case a hexagon, and it turned out to be 6. Okay, now the circumference equals 2 pi r. Okay, so if we divide the circumference by 2, so divide this sum by 2 in line 19, we get our approximation for pi. I'm going to delete this cell here below. Escape X deletes a cell. Escape X deletes a cell. And we get this approximation for pi, which is 3. Now, if we go from 6 to, say, 10, so we get a 10 gone, we get a better approximation for pi, which is 3.09. If we go to 20, then we get a much better approximation for pi, 3.12. If we go to 100, then we're getting much closer to pi, etc., etc. Now, this is in no way the operational way in which you'd want to calculate pi if you're really calculating pi. It's inefficient in many ways. We've used a lot of memory for these distances, etc., but it's very straightforward. So we start with our triangle, and if you would think that all circles are triangles, then pi would be 2.59, etc., 2.598. Okay. If you think that all circles are squares, as you do in the Flintstones if you use square wheels, then pi is 2.82, etc., etc. And I think this can drive quite a big message home with students, but then if you take your 100 gone, which one would really have to zoom in to see what's happening, and of course that zooming in doesn't work here because of just the screen is, there's not enough resolution in terms of the pixels where the screen plots us in, then you're getting a good approximation for pi. And yeah, you can even go a bit crazy and take 1,000, and you can do even much more, and you get closer to the real pi. Okay, so that was our circumference-based method. And now let's do something different. Let's use areas. Okay, let's use areas. Again, in a very pictorial, graphic way. And for this, what we're going to do is we're going to actually draw a quadrant of the circle. In this case, it's going to be the lower right quadrant. Okay, so first of all, I just want you to see, I'm going to create something. I'll do m equals rand, say 10, 10. So m here in this new cell, oops, sorry, escape L, m created in line 1 is going to be a 10 by 10 array, which is what we would call a matrix. It's a 10 by 10 array of uniformly random values between 0 and 1. So the two arguments to the rand function, which is a built-in function, are the dimensions of the rand that's going to be created. In last week's video, we dealt with random numbers, and we actually created them from first principles, but now we're just going to use the built-in rand, which is a very good thing to do, probably. Okay, we can now use a function called matchShow, which came with the PyPlot package on our matrix M. Yeah, so this, if you're just running this cell, it won't work unless you do it using PyPlot to tell the Julia kernel that you're using PyPlot in this session. So you want the commands from PyPlot in this session. Now, what matchShow does, it actually plots the values of this matrix using colors, where each point in the matrix is represented by a big pixel of this color. So look, for example, if I go to M2, 4 and make that 20, okay, so I'm going to go to index 2, 4 in the matrix and give that a value of 20, then what we highlighted is this color, 2, 4, is going to be 20, and matchShow decided that 20 is much bigger than all the other values because all the other values are between 0 and 1. So it put that in yellow and the rest are in this dark purple. It would make 2, 0 only 2.4. It's going to look like that, etc. So this is, for example, the point 2, 0. This is a point 10, 10. Let's also color that in 2.4. Okay. By showing this to students, there's already a huge message to be driven home, and that's that pictures are actually matrices, if matrices is something you speak about. But speaking about matrices is typically not done until kind of towards the end of the high school years. Still, it's kind of a nice thing. A picture is a matrix. And this is, in a sense, a random picture, except for lines 2 and 3, where we kind of change the picture a bit. So why don't we create a picture of a circle, or at least a quarter of a circle? How do we do that? How do we create a picture of a circle? So instead of getting a random set of values, let's just use the zeros function first of all and just get 0 values. And in a second I'll delete those lines 2 and 3 too. So what you see are 0 values for everywhere in the matrix except for the coordinates 2, 4 and the coordinates 10, 10. What we want to do is we want to now systematically run over every point or every pixel in this matrix and ask if this pixel lies within the circle. In this case, it's going to be the lower bottom quadrant of the circle. Okay, then let's paint it with a 1 value. Otherwise, let's paint it with a 0 value. Okay, so how do we do that? Well, there's different ways to do that, and I'll do this in a rather brute force way, and I'm going to loop over, and if you don't mind, let me just call n the variable, which would be the dimension here, just so we can then play with it a bit more. So I'll change this to n. So we let the I index be the row index run from 1 to n, and run over all rows, and within that we'll run over all columns. This type of construct that you see here between lines 4 and 8 is what you'd call a nested for loops. So line number 6, I am line number 6. Okay, so line number 6 is executed n squared times. It's executed for every I and for every j, where I runs from 1 to n and j runs from 1 to n. So more precisely, lines 5, 6, 7 are first executed for I equals 1. And then they're executed for I equals 2. And then they're executed for I equals 3. And within that, lines 5 to 7 are executed for each j. The point is that we can do this, and we can now run over every index of the matrix. Okay, these are the indices of the matrix, 1 to 10. And let me change the variable of the matrix, just I'll call it mat2. Simply because having m as a variable name for something which is a matrix, and n which looks very similar to n to have a scalar is a bit confusing. So let's call this mat. The choice of variable names when you're kind of programming a bit more is a big important thing, and you want to call your variables in a way that's understandable. But okay, let's just do that. All right. So now what we want to ask is we want to ask if I comma j in circle. This is not real Julia code. This is just what we want to do. If ij in circle, then the matrix at the point ij, let's set that to 1. Right, before it was all zeros. Now, how do we ask if ij is in circle? Well, again, we would use Pythagoras theorem, the distance formula, whatever you want to call it. You'd say if I squared plus j squared is less than or equal than n squared. So this is going to be a circle now of radius n. Circle of radius n where n happens to be discrete, then the matrix ij equals 1. Okay, ready to run it? Let's do it. Shift, enter, and whoa, we've got ourselves a pixelated circle. Okay, so lines 4 through 10 ran over every individual element of this matrix of data points, and for each one they checked, is the point in the circle or not? And for those that are in the circle, they made the matrix at that point 1, otherwise 0. Just so you see the matrix, I'll print the matrix. You see the matrix has 1s around the origin and 0s below. That's our lower quadrant of the matrix, right? You see the 0s, like at this point it's a 0, whereas all these are 1s, etc. Okay. Look what happens if I do n equals 100. So we get a 100 by 100 matrix, a matrix with 10,000 values. Extremely wasteful in terms of memory. I mean, not the end of the world with today's trunks computer, but still, you got 10,000 values, 10,000 floating values in a matrix just to draw this circle. Okay. And now maybe let's count how many points in this matrix are 1. And that would be the area, or the approximate area up to pixelation, let me call it, of this quarter circle. So to do that, all we need to do is we need to do the sum of mat. So the sum function is going to just sum all the individual entries of mat, and it's going to give us a number, and it'll say, out of these 10,000 values, how many are, I'm going to delete this cell, how many are 1? And it turns out that 7,754 values are 1. Yeah, just so you see it, if we're going to a circle of radius 10 pixels, which is of course a bit of an ugly circle, but it's a circle, then 69 values are 1. So if we were to do that and to divide it by the total number of values, now how many elements are there? Well, we can either do the length of mat. Look, we can do length of mat and we'll get 100. Or we can write here n squared, which we'll do here. N squared. So if we do that out of n squared, we get the fraction 0.69. So this is the area of the quarter unit circle, if you'd like. And if you multiply it by 4, guess what you get? Your approximation for pi, which in this case was 2.76. Let's increase to 100 and see our approximation. And we already get a quite nice approximation. This is in no way a deep mathematical method, but it's at least a method which shows students what is a matrix, what are points in an image, how you actually create an image using this formula, how this distance formula creates an image, because it defines the points which are not greater than n in their distance to the circle. And yeah, if you're going to 1,000 by 1,000, so you got to be responsible. Don't keep in mind that with 1,000 by 1,000, your matrix now has 1,000,000 values. So we now have 1,000,000 values, but Julia can still handle that. And we get a pretty nice approximation to pi. Okay, so this was how we did it using area in a brute force manner. And now let's go to one more method, which will be using a similar concept, but just using a bit of randomness. Okay, so we used randomness earlier just to exemplify what a matrix is, but we didn't use randomness to approximate pi here. So let's do something with a bit more randomness. So look at this. I'm going to create a set of points, and I'll call each point a rand, comma rand, for I in 1 to n. Let's take n to be 10. So what I took here is 10 random points where the x-coordinate is random, uniformly random 0, 1, and the y-coordinate is random. Actually, in this comprehension, by the way, I don't have to specify I or k or anything like that, because notice that I don't use it here. So I can just say for underscore. That's just a bit more verbose or explicit in the sense that I'm not using that index variable of the comprehension. Okay, so these are 10 points. Now we know how to plot, right? So we can plot the first of those points. I'm applying here this broadcast operator to the first of points. These would be the x points, and the last of the points, that would be the y coordinate of the points. And let's plot actually points. Let's plot them as points. And what we've got is 10 random points in the interval 0, 1. Let's not go for 10, let's go for 100 points. We've got 100 points in the interval 0, 1. And if you don't mind, I'll copy these lines from here, the subplot 1, 1, 1 aspect equals 1, just so we get our aspect ratio to equal exactly 1. Okay, so we've got an aspect ratio of exactly 1. We've got the interval 0, 1 on the x-axis, the interval 0, 1 on the y-axis. So we've got this square, and we're plotting 100 points in the square. Let's even plot 1,000 random points in the square. Let's plot 1,000 random points in the square. Now, just like we used here, and just for convenience, we went for the bottom right quadrant, and that was just because matrix indices go from the top left in the way they're presented. So let's think here that this is the top right quadrant of the Cartesian plane, as it is, and there is a circle inside here which we want to find. Now, where is the circle? Well, the circle is going to be defined by all those points that are with a distance to the origin of less than or equal to 1. Right, let me even take 10,000 points. So we've got 10,000 points. That's maybe a bit too much, but that's okay. We could stay with it. Oh, let's go back to 1,000, just so plotting is a bit quicker. Okay, so I actually want now for each individual points in this array of points. So I've got an array of points, and I want for each individual points, I want to ask, hey, point, are you in the circle or not? Hey, point, are you in the circle or not? I want to ask this for each point. So for this, let's create a helper function. There are better ways to do this, quicker ways, but again, I'm taking kind of a first principle approach. And we'll call this function inCircle. So what this does, this function gets a point, and it returns true if this point is in the circle, and false if it isn't. Well, how is it going to do that? It's going to take the x-coordinate squared plus the y-coordinate squared, and it's going to ask if that's less than or equal than 1. And this will be the return value. Okay, that's going to be the return value of the function. Now, just to show that things can be written in a slightly shorthand manner, I won't even do that. I'll just do this, and this is a shorthand manner of writing kind of one-line functions. Okay, that's inCircle point. Let's just see that our function works. Let's do inCirc of the point 0.2, 0.2. 0.2, 0.2 is in the circle, right? So we should get a true. How about the point 1.2, 0.2? That's outside of the unit circle, and that's a false. Once we've done that, we can now use a built-in Julia function, and let's get the help for it just so we see it. That's the filter function. And what filter is going to do, filter is going to get an array and it's going to apply the squarey function f to every element of the array. For example, in the example that they show us here, we're using the function is_odd. So the function is_odd is passed as an argument to the function filter, and the array A, in this case it's a range. The range 1 to 10 is passed to filter, and filter only keeps the elements of the array which satisfy this function, or this questioning function, meaning for which the value is true. So if we were to do filter with our new function in circle 2 points, and we'll call this the circ points, what we're getting now, what we hope, is that circ points, that these lists of the points are out of those random points, those are the points that were actually inside the circle. Let's plot those points. So let's duplicate line 4 here. I'll copy line 4 and paste it here below, and instead of points I'll put circ points and circ points. Let's make sure line 4 is with blue and line 8 is with red, and let's see what we get here. That's kind of cool, no? So for every random point, we're actually plotting here the red points over the blue points, but that doesn't matter. Okay, so the blue points which you see are the points for which in circ returned false, and hence they didn't make it to the list circ points, whereas the red points are in the list. Just to compare, look, if I do length of the array points, we've got 1,000 points. But if I put comma length of circ points, so when you put a comma here, what this does in Julia, it actually creates a tuple, and then you can see both values together. And only 790 points out of those 1,000 made it inside the circle. Now there's randomness involved, and we're not using the same seed here. So if I run this again, I get a slightly different image. And look, then if I run this command again, I get a slightly different number, not 790, but 795. Oh, well, 795 doesn't differ so much from 790, right? Because of the law of large numbers, on average, we're going to get something which is quite close to the expected value, especially when you've got n thousand, certainly if we've had n 10,000. So now, why don't we just count how many of the points, length of circ points, out of the n, what proportion of them fit in there? Okay, and I've now got 10,000. And let's multiply that by 4, because again, this is just one quadrant, and we want the 4 quadrants. And we want, well, we're speaking about a circle of 4 quadrants. And there you have it. You've got here a Monte Carlo, or a randomized estimate for pi. You've got a randomized estimate for pi. So look, if I run this again, the estimate was 3.16. If I run it again, it's going to be 3.14. And if I run it again, it's going to be something else, a different 3.14 with more precision, etc., etc. Let me comment out the plotting for a second, just so so I can run it for a big value. So I'm going to run it now for 1,000,000 points. Plotting 1,000,000 points might be just a bit challenging for the plotting, not so challenging, but a bit, and then you get a quite solid estimate of pi. Let's even run it not for 1,000,000 points, but for 10,000,000 points, and the estimate is even more solid. It's still a random estimate, but it's a randomized way, which is consistent. So yes, I'll go back to this this blog post, which I will link to the comments of this YouTube video. Monte Carlo simulation of Buffon's needle. That is a slightly neater way of doing that, and this has some cool analysis. And the idea here is that you throw a needle, not a point, because physically I don't know how to throw a point, but I think I know how to throw a needle, and that's the idea of Buffon's needle. Okay, I'll finish with this plot here and go to 10,000 points again. and go back to the top of the notebook. I'll tell you that all these notebooks are available on the community page of 1 on Epsilon. And if you like this video, please do the following: subscribe to our channel, and follow us on Twitter, follow us on Facebook, and look at Epsilon Stream. So this is what we're really here for. So our completely free platform, Epsilon Stream, that's a team of people that we work in 1 on Epsilon. What we do in Epsilon Stream is we collect a variety of resources from the web, many of which are YouTube videos, and we present all those in a single, unique, clean experience where you can search for almost anything in the world of K-12 and exploratory mathematics and get the content and videos that we selected in the way that we think is best. So just head on to 1onepsilon.com, register with us, and follow us using other ways in social media. So I'm Yoni Nazarathi. Thanks a lot. See you next week. Bye.